Okay. Hello and good afternoon. I think we can start. Have started recording. Please just let me know if you can't hear me or if you can't see the slides. I'm going to share the slides now. Hopefully it should be all good, but let me know if it is not. Okay. So this is the I think the third workshop that I have been covering, and in today's workshop, they're going to talk about evaluation metrics. So I don't think evaluation metrics necessarily need a lot of motivation, but let's make it clear why this is an important topic and why do we need different metrics before going into the different metrics that we are going to talk about today. So so far into the project, hopefully you have been able to get some results. You have basically processed your data set, you have found out what model you want to use. And now that you have got some initial results, at least you want to be able to measure how well your model is doing. So that measure needs to be something quantifiable. You need to put a number on the performance of your model, no matter what your task is. Whether you're doing language processing, whether you're doing stock prediction, image classification, whatever you will need to be to put a quantitative number on the performance of your metrics, and that normally has two main basically reasons or motivations. First, if later on you will improve your model compared to this first initial version that, let's say you call it a baseline, if you introduce some improvements, you want to be able to see over the numbers how much improvement you have got. Or if there are already, if you're using a public data set, you need to be able to compare with the numbers that other people have got to see basically if you are getting up to the expectations or not, if there's any problems. So the other good thing probably about putting a number is that if that number is very off from other people on the same task, using the same method, then you would know that there is something going wrong. So it's always a good thing to be able to quantify the performance of your method and be able to compare that with other things, other methods or other previous baselines. So one thing that we need to clarify here, it's very important. Sometimes there's a little bit of a confusion around these two, is metrics versus loss. So in most of the machine learning algorithms, we normally have a loss function that we try to optimize in order to find the best parameters. So for example, if you're using neural networks, you will feed your input to your model, you will get an output, you compare that using a loss function with the expected output if you're using supervised learning, for example, and you will get a number in terms of how your model is doing. And then you use that function, that number, to calculate the gradient, and you use the gradient descent to back propagate and update your parameters, update the parameters of your model. So then in that sense, it is normally, so that loss function needs to be differentiable, and it is normally used during the training, sometimes during the validation, to also check the performance of your model. For example, check if it is overfitting or not. But then it's mainly used during the training to update the parameters of your model, right? It's used for learning. Whereas the metric is some sort of measure that after you have finished training, after you have done validation, after you have figured out if there is overfitting or not, you have come up with the model that you want to test, normally on a testing set, and you want to see how good it is, how well it is performing. So in that sense, there's a difference in terms of when these two different functions are used. Both of them are functions. The difference is that the metric doesn't have to be differentiable, for example, because you're not getting the gradient, you're not getting the derivatives, you're not doing optimization on that, whereas a loss most of the time has to be differentiable so that you can update your model. But the thing is that the same function can be used as both. For example, mean squared error, if you're doing a regression task, you might use mean squared error to update the parameters of your model. That's where you call it a loss. And then after you have got your results, you also get the mean squared error to compare with the basically get the performance on the test set and compare it with other methods. So yes, it can be used as both, but there is a very fine line between these two, whether we are talking about a metric or a loss. And the topic of this session is the metric. We assume that you have a model that is working. Now we want to quantitatively measure the performance of that model. So depending on the task, some of the metrics, of course, are used across different tasks, but there are also some metrics that are specific to different tasks, depending on what you're doing. And here we have tried to basically put a few different metrics together that covers a range of tasks. So if you're doing classification, now that classification could be in language, could be in images, could be in speech, it could be many different tasks. If the task is on many different applications, but if the task is classification, normally there's like a few famous metrics that people use: accuracy, precision, recall, the one that we're going to see, and the confusion metric. So again, like a small note on confusion metrics, I wouldn't personally consider that as a metric. It's like a matrix that is used for visualizing some of the metrics. Like you see on the confusion matrix, the precision and recall, true positive, false positive, those kind of things. So by itself, it's a matrix that helps with visualizing some of the metrics. I wouldn't consider that directly a metric, but it's a good way to see the other metrics that we mentioned. For regression, normally you would use mean squared error, also known as L2. When you're talking about the loss, it's normally called L2 loss, but it's the same thing. Sometimes you also have L1, which is like the non-squared version, which is the absolute difference. But this is just a popular example. And then there's R squared metric. If you're specifically working on computer vision tasks, such as image generation using GANs and those kind of things, or you are doing object detection, segmentation, there's IOU, there's SSIM, inception, score that we're going to talk about, and finally NLP. There are precision and recall can still be using NLP, as I suggested before, in some of the tasks, but there's a more kind of dedicated metric that is used in NLP called BLUE. Although this is not another general note is that these are the list of mainly popular metrics, but they all have pros and cons, and it's really your job, and it depends on the task which one you want to use. I would call this list a good starting point rather than an exhaustive list of all the metrics. So that's important to know. So now moving to the classification tasks. So as I mentioned, you could be dealing with many different things in the different areas, different application. You could be dealing with images. You could be. So this figure should not be on top of this. Let me fix this. Okay, this should be going down. Go back to this again. So whether you are doing image classification, sentiment analysis in NLP, which is still a classification task, or activity recognition if you're dealing with videos, all of them are considered classification, and the same basically metrics apply. The simplest and the most straightforward metric to use, probably the thing that you want to always have and always start with, is the accuracy. And the accuracy is measured as the number of correct predictions over the total number of predictions. So if you have a test set of, let's say, 1,000 samples, and out of those 1,000 samples, again, if you're doing classification, which is supervised learning, if you are correctly predicting 500 of those, you're getting 50% accuracy. So now, one thing that you have already noticed probably is that we are not talking about class specifics, right? When we say accuracy, it's not clear whether we are doing binary classification, multi-class classification, multi-label classification, how many classes we have, what is the performance inside every one of those. These are not the things that we can see in accuracy, and that's a major problem. Although it's a good starting point, you might want to quickly see, okay, what is a global measure of the performance? You would most of the times need to be more specific if you are dealing with especially multiple classes. What could go wrong? Something that most of the times, at least from my own experience, goes wrong is that there's a high chance that if you're training a model, that model collapses to a single output, especially if you have imbalanced data. That's very common. So let's say, again, out of that 1,000 samples that you have during your trading, 900 of those are from one class and 100 is from another class. There is a high chance that if you don't do everything in the right way, and sometimes it's a challenging task really, your model will learn to output only the class that has seen 900 samples of those. And then you would get 90% accuracy just by outputting a single constant value. But your model is basically performing very bad because you're ignoring the other class completely. So it's important to go a bit further into the details, and those details could be further clarified with precision and recall. Now in scikit-learn that we have always been in the past two workshops talking about, a lot of these metrics, most of these metrics that we are going to talk about are available through scikit-learn, and it's easy to use. So if you just import them using this scikit-learn metrics library, again, here we are talking about accuracy, so it's the function is called accuracy score, and then what you would need to do is just basically input your predictions versus the ground truth, or better called ground truth versus the prediction. So first array is always considered the ground truth. Second one is the predictions of your model, and that's the list of IDs. For example, if you have binary classification, it's list of zeros and ones, or a numpy array of zeros and ones. Now, precision and recall, what are those? In order to get to precision and recall, you need to first calculate 4 different values: true positive, false positive, true negative, or false negative. Well, actually, true negative is not here used, but you could, it could still carry important information about basically the number true negatives is basically the ones that you didn't predict and you were not supposed to predict. You did a good job by not predicting them. So I think these are fairly clear, but true positive is basically the number of samples that you were supposed to predict as a specific class and you did predict correctly. False positives, the ones that were from another class, let's say they were supposed to be class 2, you predicted class 1. Those are false positives for class 1. True negatives, again, is the opposite of false positive, where you true negative is that it's another class and you correctly did predict another class, did predict the same class. So you were not supposed to, let's say it was 2, you were not supposed to predict it as 1 and you didn't. False negatives is the samples that you did not predict. So let's say there was a sample that you were supposed to predict as class 2, you did not predict 2, you put a 1 on that. So it's the negative examples, the ones that you missed in your prediction. Now, with a diagram, it would be more clear, but the formula is like this. Precision basically tells you among all the predicted positive values for a specific class, how many of them were correct. So if you, let's say, predicted over the whole $1,000 set, let's say, you predicted 100 class 1, and you had altogether in your ground truth, you had only 50, let's say you had 200, then you have got 50% precision. So the number of correct predictions versus the overall number of basically all the number of predictions that you have for that specific class. So it might have been a bit confusing, but I think basically the formula itself is very clear. True positive over the true positive plus the false positives. And then the recall is true positive over true positive plus false negative. So it's basically comparing within the ground truth. So the number of correct predictions over all the ground truth predictions. I think I made a mistake between these two. So apologies for that, but what is important is this formula. Now it would be clear a lot more clear on this basically Venn diagram. Let's say you have this whole set of true negative, which is all the set of values that you were supposed to predict and you didn't. Then the ones that you have basically predicted correctly is the overlap between all the set of predictions and all the set of ground truth. So that's called true positive, right? If let's say the blue diagram is all the ground truth, and let's say the yellow diagram is all the values that you have predicted as a specific class, then the overlap is the true positive, and the ones that you have predicted, but they were not part of the blue diagram, they're false positives, and the ones that are in the blue diagram, but you did not predict is the false negatives. And then basically the precision and recall would be this true positive among either of these. So if you're calculating the true positive over the size of all this blue diagram, you're getting recall. And if you're calculating the true positive over the yellow diagram, you're getting the precision. Calculating it over scikit-learn, again, they are part of the metrics library, and they're called precision score, recall score, or you could also use this classification report, which the good thing is that it gives you everything, including the F1 score that we're going to talk about. So this classification report is a full report that gives you precision, recall, F1 score, and also, I think, accuracy, which is missing here. You can see the accuracy as well. So these precision and recall are very good. They give you more insights into the performance of your model per class. But what if you have multiple classes and you want to report a single number that considers all these things? So it works better than accuracy in the sense that it is separating the class per class metrics, but it's still a single number. So that's basically where the F1 score comes in. And what that is basically the average, the harmonic average, they call it, of the precision and recall. And the formula is 2 times the precision multiplied by recall over the sum of precision over precision plus recall. And as you saw, it exists in the classification report. You could see that, and or you could separately access it using the F1 score function in the metrics library. So again, what it does, it puts basically it's an average of your precision and recall. So it's like considering still per class, but going specifically after the precision and recall and putting a number on those. So it would still provide more information as per class, but it is a bit more detailed. It carries more information in terms of considering the recall and precision. There could be still a few problems in this one, and that might be the reason that if you want to check other metrics furthermore, like there is weighted F1 score or F beta score, sometimes they call it, but normally this would suffice for most of the applications. And as I mentioned, the problem with this one is that it puts equal weight, for example, on the precision and recall. You're saying precision and recall are equally important for me, which is not true in some of the tasks. So if you are, for example, I don't know, you're detecting something that is very important. So for example, let's say you are detecting a fraudulent transaction in banking. So it's very important for you to have a very high recall, although the precision is also important, but you don't want to miss any fraudulent transaction because basically you're allowing that fraudulent transaction to happen. So in some cases, one of the precision and recall might be more important. So you might want to have a basically metric that stands for that. Now coming to that confusion metrics that I mentioned, again, it's mainly a summarization of the precision recall, true positive, false positive, and true negative comes in here. So the diagonal values are the ones that you might we want to get 100% over, and you want to ideally have basically 0 false positives as 0 false negatives. And if you calculate the sum of, if these are basically actual numbers, not normalized, if you get the sum of, and if your x-axis shows the true class and the y-axis shows predicted class, this is doesn't really matter. You could swap these two, but if that's the case, and of course, if you swap them, the position of true positive and stuff would change. But what I'm trying to say is that that's not a set in stone. So sometimes, depending on how you calculate it, you might have ground truth on y-axis, but this is more typical. Anyway, if this is the confusion matrix that you have and it's not normalized, then some of the rows would show you the precision and some of the columns would show you the recall. And the reason is the formulation of the recall and precision that we saw before. What is good for, as I mentioned, in a glance, especially if instead of numbers, we saw in the matplotlib you could use heat maps, and then in a glance you could it carries a lot of information, especially if you have lots of classes. Then you would in a glance see that all your diagonal values, if they are, for example, if you're using heat maps, if they're all red, it shows that they're all high. Then those colors would basically carry a lot of meaning, and it's quick to understand. One thing that you want to note is that when you have multi-class classification, then even in the accuracy, or if in recall and precision, what matters is the way you average these metrics over the classes. So there's a few different ways that you could do the averaging. It's either weighted averaging or it's macro averaging. Macro averaging, basically all the recalls have the same weight, and then you just divide it by the whole set. Whereas if some of the classes are more important for you, you could have weighted average. And again, there's an example here that depending on your predictions, the weighted average and macro average could be very different. So it's really for you to dig deeper in your specific application and see if you have these sort of importances. If you have imbalanced data, you might want to make sure that you use a metric that clearly shows what is going on inside every class. And if you're aggregating those in a single number, that number is good representative. Otherwise, it might carry the wrong message. You might think, for example, you get 90%, and you might think, oh, that's great, I'm happy. But you dig deeper and you realize that, okay, you're in one of the classes, you're not getting the performance that you want. Getting a bit away from accuracy, precision, and recall, although the ROC curve is kind of related, but in some of the applications, you have a threshold value that you can play with, and that threshold value would define the precision and recall that you get. A good way of visualizing that is something called receiver operator curve. And it's not just a visualization. Sometimes you also want to tune that threshold parameter to probability parameter that you decide if a specific value is a true positive or a false positive. And you could see, for example, ideally what you want is that as you increase that probability threshold, you would see an increase both in your true positive and basically you get a false positive rate or the recall. So it's important not to get confused here. I was getting confused for a second. So the recall is on this one, true positive rate, and then the false positive rate is, let's go back to this. So you have the recall here, which is a true positive rate. It's not the true positive itself, it's true positive over the sum of true positive and false negative. And then the false positive is the number of false positives that you have. So if you increase that threshold, ideally, what would happen is that as you get a higher true positive rate, you would also see an increase in the false positive rate, which is not a good thing. So ideally, you want to have high true positive without having basically very high true positive values. So you want to stay around here, that you have like 100% true positive rate, where your false positive is still around basically zero, as close as possible. Whereas in practice, what happens is that as you increase that threshold, you add more you add more false positives. And let's say if you want to get 100% true positive, you would also get 100% false positive, and that's not a good thing. So you want to raise this level basically as high as possible, and make sure that you have ideally, as I mentioned, high true positive rate without having any false positives. So this ROC curve, and then the next one, the area under that curve, is another metric that shows you basically how sensitive your model is to that threshold and what is the best performance that you can get. As I mentioned, ideally you want to get an area under the curve of 1, which means that your curve will be like this. It goes up all the way to 1, which means that you will have 100% true positive without having any false positives. So this is another way to both tune that threshold and see how your model is sensitive to that. So I think with this one, basically, that was I think a good summary, a good starting point for dealing with classification tasks. And then for the next one, we move to the regression task. We're going to see some example metrics that you could use if you're dealing with regression. So an example that I have come up with, which is probably close to mind, is where you are trying to predict stock or house prices. These are a lot of things that you see on Kaggle, for example, but it doesn't have to be this one. So most of it, there is also a chance that you want to predict something from the images, a specific value, let's say the size of a tumor or the rotation of a tumor. So these are the tasks where you're dealing with regression, in the sense that from your input, you're predicting a continuous output. Instead of saying which class it is, you're directly saying which value it has. Although one note here could be that there is also ways to convert your regression tasks to classification. For example, in the let's say in the house price prediction, instead of saying exactly if that house is $100,000, you could say if it is between 100 to 200 or between 200 to $300,000. So you could always basically quantize your values and define your task as a classification. Now that has pros and cons. I'm not suggesting that you should always do that. Because when you convert it to a classification task, basically you are saying all the classes are equally important for me in terms of the loss function that you use. If normally you use cross entropy, then a house that has 100,000, it's worth 100,000. There's equally likely that your model could predict that for 100, and that's not a good thing. Whereas if you're dealing with regression, normally if your model is doing a good job, the value should be closer to that thing. So you're losing that order in the values that you're predicting, but sometimes is a good choice. Again, let's not diverge from the main task. So if you're dealing with regression, then there are a few things that you could do to measure the performance of your method. The simplest way that probably is a very good starting point is to basically visualize the predictions of your model. Here we see like a code snippet that is using the Boston dataset, ridge regression, and like the purpose is to see how to plot these two predictions versus the ground truth that you had. But what you would want out of this is ideally you need to have a basically one-to-one relationship between your predicted values and the ground truth. And by that I mean a line that has a slope of 1. So that's the idea, right? If your predicted value is 30, or if your ground truth value is 30, ideally you want to predict 30. And if that's the case, then it means that you have like a line of y equals to x with a slope of 1. There might be sometimes biases in your data set, that's fine, but the slope is very important, and that quickly shows you if you, let's say, if you predict, if you plot all this prediction against the ground truth, you could quickly see, okay, in around the areas, let's say in this figure, around the areas between 30 to 40, that's where your model is overestimating everything. Everything is basically predicted way above the value. Or in a smaller values from 10 to 20, you could in a glance see that your model is under predicting. So it's predicting under 10. So those are the things, and the amount of variance that you see, for example, again, it's very likely that your model learns to predict an average of your data set. Then you would see all the predictions are around here, and that's not a good thing. So this kind of visualization, again, it kind of goes back to the first session that we talked about visualization, but from experience, that could be a good starting step to see before putting a number on your model, or even after putting a number. This clarifies a few things about, again, where is the area that your model is not performing. So I think it's always useful to visualize the performance using the predicted against the ground truth. Now, the purpose of this session, of course, is not about visualization, it's about putting a number on it. Now, if you want to put a number, mean squared error could be, again, as I mentioned, it's briefly in the beginning, it's known as L2 loss. It's very popularly used, and the formulation is basically the average of the difference between the ground truth and your predicted squares. So it's the mean of those squared distances between your ground truth and the prediction of your model. Now, one potential problem that this might have is, and in this figure below, we can see an example. Let's say I tell you that your mean squared error is 100. Now, the plots for that could be either the left one or the right hand side. It depends on the range of your values that you're trying to predict, right? If your range of values, for example, in this plot is between 10 to 50 or 0 to 50, or if it is between 0 to 100, or even if it is in ranges of thousands, that affects your mean squared error because that depends on the actual values that you're predicting. And what that means is that the same performance on the right hand side, it's a very good performing model, whereas the left hand side is not performing well. It's the predictions have high variance, they are spread all over the place. So the mean squared error, the message I'm trying to say is that mean squared error, if you have good understanding of the range of values, it could give a sense of how the model is performing, but it still doesn't carry any information about the variance of your predictions. Now, a note again on scikit-learn metrics, you could use mean squared error, although this is not too difficult to implement in NumPy, but I think even in scikit-learn it's using the NumPy backend. You basically pass the predictions and the ground truth values, again similar to classification, and it gives you the mean square error. Now, if you want to go a bit deeper and get a better sense of how your model is predicting, and if the variance of your predictions is important for you, then you might want to use R squared metric, and it's sometimes known as coefficient of determination. What it does is basically, apart from the fact that we have the formula here, 1 minus the square difference between the ground truth and the actual predicted values over the mean average, a mean distance to average. So mean square distance to the average. So you're basically comparing how your model is performing against a model that is outputting an average. So you want to see how better or worse than average you are, because normally in regression, the worst case scenario that your model should be able to do, except if it is completely off, if it is predicting something, if it is not learning anything about the data. Normally, your model starts with an R squared of 0, and that means that your model is predicting the average. So if your model is predicting the average, then these two will be the same, and you will get a 1 here, and R squared will be 0. But in practice, it is possible to be negative, and as I mentioned, the one reason could be that your model is, the variance of your model is way bigger than the distance to the mean. And then this value becomes more than 1, and then you will have a negative R squared. Practically, it's possible, but normally in regression, the baseline is to just output the average. The model should be able to ideally learn the average. And that means a 0 of R squared. And then you would need to, as your model gets better than predicting the average, then that average doesn't have any variance, right? Your output has 0 variance, and that's not a good thing. You want to make sure that as much of the variance in your data that exists, you basically represent that variance in your prediction as well. So as much of the variance that exists in the data should be presented in the prediction. And that's the purpose of this metric. And as I mentioned, the better that variance is represented in your predictions, the better, the closer to 1 you would get. Again, quick note on the scikit-learn in metrics library, it's called R2 score, and passing the ground truth and the predictions. Now going back to the initial slide about regression that I had here, what I wanted to note is, I think I briefly discussed, but you could also put a number on the, you could also compare your model in terms of mean and the slope of this line compared to the ideal line that is a 1, right? As I mentioned, if you are ideally predicting everything correctly, then if you fit a line over your predictions over this plot of prediction versus ground truth, that line should have a slope of 1. So what you could do, if you could fit a least squares regression on this plot as well, and then that slope, how far away from that slope you are, it would give you a better sense of how your model is compared with the ideal, which is a slope of 1. So those are kind of the most maybe commonly used. Again, please note that it's really application specific. Sometimes we even didn't introduce the mean absolute distance. It's very similar to the mean squared error. It's just that there's no square. It's the absolute distance between the points. So it might be good to sometimes it's good to just check all these metrics, and because every one of those send a specific message. Sometimes you want to stick to a specific one of those. So it's really your job. And again, the purpose of this workshop is to provide more of a starting point rather than a finish line or exhaustive list. So let's move to the some of the basically metrics that are more specific to computer vision tasks. Also IOU, for example, you could have IOU in terms of if you're dealing with 2 arrays, let's say. But these are typically used in so we are here interested in the typical metrics that are used in some of the common computer vision tasks. So for example, if you're dealing with detection and segmentation, normally the way to put a number on the performance of your model is the first step is to calculate this IOU, which is intersection over union. And as the name suggests, it's also known as jacket similarity. As the name suggests, is basically the amount of overlap in your or the intersection of your predictions. If you're, for example, on the left-hand side is segmentation, you could, if this is your segmentation mask, the yellow one, and this is, of course, the bottom one is the ideal one. You put these two over together and you count, for example, the number of pixels that these two overlap, and that's your intersection. And you count the number of pixels that these two, that the union of these two has. And that will be your union, intersection over union. Dividing these two gives you the IOU measure. Or on the right-hand side, if you're dealing with object detection, you are having bounding boxes, then it's the same thing on the bounding boxes. You need to measure the area in the intersection of those two bounding boxes and the area in the overlap. And again, ideally, you want to have, this is a metric between 0 and 1, and you want to have one as close as possible to get to basically to get as close as possible to the ground truth mask in segmentation or bounding box in detection. Now, just having the IOU normally is not what people report if you're using any of the segmentation or detection. What we do is we use that as a threshold to decide if a prediction is good enough to be considered a true positive, or if it is not good enough and it needs to be considered a false positive. Let's say here you say, oh, I'm happy with this prediction on the left-hand side. It's close enough with the person. So you define a threshold of, let's say, if it is above 30%, then I'm happy with that. I would consider that as a true positive. Same goes with the bounding boxes. You put a threshold on this IOU normally, and you say, okay, anything above, let's say 70%, they look good enough, they're close enough, and they're considered true positive. And then if you have that, then basically you could go back to any of those classification metrics and report them on these true positives and false positive rates that you have calculated. So along with IOU, one note is that sometimes people also use, in object detection is commonly used probability confidence threshold. So not only it's about the overlap between the ground truth and the prediction, but it's also about how confident your model is. If it is giving, let's say, a very good even overlap, but it is very unconfident, let's say it gives 20% confidence, sometimes you might want to ignore that because you want to increase the confidence of your model as well. You want to make sure that your model gives maximum confidence to that specific class, because of course you might have multiple classes whether you're doing segmentation or kind of dip detection. So as I mentioned, then you could add this IOU or Jakarta score, which is again, as a note in scikit-learn, it's called Jakarta score. And here, because you might have outputs as masks and images, you could have 2D arrays, and it calculates the overlaps and gives you the Jakarta score. So as I mentioned, you could use IOU along with probability distribution, and then you could define the average precision, average recall, the way that we saw before for classification. People commonly use, for example, mean average precision, and that's first average over the classes and then mean over all the samples. That's called mean average precision, or mean average recall also exists. So that's for two of the tasks. If your task is if you're using a generative model for a task of image generation, no matter what that image is, there is different ways that you could, this is a bit more difficult. This is an open area of research. People are still trying to find better and better metrics. Although very good metrics have been introduced recently over the past couple of years, but it's a bit more difficult to quantify exactly. But sometimes people use manual human inspection evaluation. Sometimes people, for example, use in public data sets, use mechanical Turk, for example, to associate a lot of human annotators, mark, or qualitative assessors to basically assess if the predictions or the generations, here we're talking about generative models, if the generations or the samples that the model has generated are good enough. So you could see different examples here, and here is showing a metric that is commonly used. But apart from that metric, what I'm trying to show here is that your model could have different sort of distortions, could have and if the ideal image that you want to predict is this one, for example, it could be distorted like this, or like it could be completely off. And then we need a metric that deals with all those. Or if it is blurry, it's not high resolution, or if it has black spots, there's different kind of possibilities. Or if it is supposed to predict a specific class or a specific type, and for example, it was supposed to generate a female image, but it generated a male one, or in total unrelated ones. Those are the different things that we need to be able to quantify, and it's a fairly more challenging task. So apart from the human evaluation, there are some metrics. I have put like a categorization of direct, indirect. It might not be 100% true. This is more of my personal opinion. But indirect, it means it is indirect in the sense that you could basically feed the samples that your model has generated to another model, another predictive model, or another discriminative, better call it, model, like a classifier, and then you get a measure of how good that classifier performs. Of course, here the problem is that you're assuming that classifier is doing a perfect job, but of course, most of the times that's not the case. But you're relying, if that classifier can classify that, and of course, another note is that we have seen examples that these classifiers, image classifiers, for example, are noise sensitive. We have this topic of adversarial attacks to classifiers. So they're sometimes easy to fool, but let's assume that they're doing a good job. Then you could use the performance on those classification, as you're going to see, for example, and put it in a structured way. People call it inception score, to be able to quantify the quality and diversity of these images. Or there's also, for some of the tasks, it might also work to compare the statistics of images. If you have the pairs of images that have ground truth and the one that it was supposed to be generated, then you could use SSIM, and we're going to see what that is, which is basically comparing the local statistics of the two images. Another thing to note is that what is the objective here? So if you are having a model that is generating samples, not only those samples need to be good quality, need to look good, need to make sense, need to not be like this image that we are seeing here, distorted, but they also need to be diverse. So for example, it's not it's not ideal to have a generative model that always predicts the same thing, or always predicts a few different samples, which sometimes people call it mode collapse. Not sometimes, most of the times. It's known as mode collapse, where your model basically is predicting the same thing. And instead of predicting a distribution, instead of learning a distribution of all the images, it collapses to modes of those distribution, people call it. But let's don't get diverged again. The takeaway message that I was trying to say, or the message that I was trying to convey, is that there are two things that are important when you want to measure the performance. One, quality, that we can visually see if they are good quality, if they make sense, if they are distorted or not, if they are following the structure that they need to follow. And also the diversity is important. By the way, there is on the bottom, you can see the reference. If you are interested in this area, there's a lot of research, as I mentioned, going on. There's a good example of evaluating all these, at least on the ones that were introduced until 2019, all these metrics. You could refer to that, and some of this stuff is also adopted from that paper. So inception score, complicated math, yes, no. What it does is basically it gets the expectation of the KL divergence between these two distributions. Oh, now that's we don't want to get confused here. KL divergence, just assume that's the distance of measuring two probabilities. Like the distance, we have distance for actual values. Here, KL divergence is a metric, not a metric, is a measure. Basically, that measures the distance between two distributions. And if we do a bit of math, we see that this inception score is basically the exponential of the entropy of the y, and y is the samples that you're generating, x is the input, minus the expectation of the conditional entropy. Now, putting that in English, what it means is that this is trying to quantify by making sure that the distance we want a high value, basically, that these basically, by making sure that the entropy of the generated samples is high, we want to have high overall diversity. And by making sure that basically the entropy of conditional samples is low, because we have a negative here. Ideally, if we want this score to go up, we want the entropy, the first entropy to go up and the second entropy to go down. The first entropy is advocating high overall diversity. So it says all the y's, all the samples that this model is generating, we want them to have high entropy, which means we want them to be very diverse. We want to have different classes, different shapes, different faces, different emotions, whatever. And then the second one says in expectation, we want to have low entropy inside conditioned on a specific input. So if you are talking inside the class, we want those samples inside the class not to be very diverse. Of course, we want them to be inside that class. So if they are too diverse, there's a chance that those samples are not considered within that class anymore. And the way they do is, and then where the name comes from is that and this was introduced in the paper that you see on the bottom again in 2016. They use an inception net, which is a convolutional neural network, to basically estimate the probability that that network assigns to that sample. So if you feed that, let's say, image that the model has generated, what is the probability that a classifier gives us for a specific class? So we estimate that probability like that, as I mentioned, the conditional probability. And then we are also interested in this marginal class distribution, which is the average of the class and the probabilities assigned again by that inception model over all the samples that are generated. So they could be outside. So it's basically all the samples that are in that class. So this is for a single sample, condition on a single input. This is for all the samples in that class, let's say that we generate. And then using those, we put them in the formula and we get the estimate of the inception score. Now, again, what is important to know is that this inception, the way it works, of course, there's available code packages that we could use to measure that. But what is important to understand is that we use another classifier inception network, and we are trying to maximize the diversity among different classes, different samples that the model is generating. And we are trying to basically keep those, minimize basically the diversity that we have within the class for every single sample. And we are also favoring the quality of the generated sample. So by making sure that that classifier is doing a good job, is able to classify them, basically is able to give good probabilities, we are making sure, so we are favoring the quality of generated samples, because if they are not good quality, hopefully and ideally that classifier should not be able to give the proper score or the proper probability, should not be able to classify them, and then that will affect the inception score. As I mentioned, with pretty much all of these metrics, they have pros and cons. One of the cons, for example, for this inception is it doesn't account for overfitting. Let's say if you have a specific data set and your model is able to generate everything within that data set very well. And if that data set is diverse enough, then you're getting good inception score. But all your model has learned is to just memorize those training samples. So there's nothing, as far as I understand, this is an inception score that basically reveals that phenomenon to you. The other thing is that it relies on the performance of inception net. As I mentioned, you are relying that inception net that is trained on ImageNet is doing a good job. And the other thing is that it's a network that is trained for image classification. It might focus on specific targets in the image, for example, the objects to classify if it is for a specific class. And it might ignore other things that are going on in the background, for example, of the image, or other things. So it does not really send you a clear message about those qualities in the image. There are extensions to that. There are better ways that stand for that. Cons, I think I have put a list of those. Again, as I mentioned, this is a good paper to refer to. There is other measures like FID, fresh inception score, if I understand, if I remember correctly, and you could basically check those yourself. But what the next category that I mentioned is the direct comparison. So let's say, as I mentioned, if you have image pairs, it's probably more clear to check these ones. So let's say on the top left-hand side, this is the original image that you are ideally expecting your generator to generate. And then for some reason, you have generated any of the other images. Now, we didn't mention this, but one way, of course, because your generation means you're generating the value of every single pixel. So you could compare the values of those pixels with the ground truth using any metric, any regression metrics that we talked about, like mean square error. And what you would see, if it is visible, hopefully, is that all these images that are clearly different in quality, but they will have the same mean square error, or very close to each other. 142 here, 144 in any of them. So, and that what that says is that comparing the pixel values is not really a good metric to see how your model is performing. And this SSIM with that is introduced with that motivation. What it does is basically chunks your image into smaller chunks and patches, just the way that you do when you do a convolution. Basically, you go through the whole image. It basically applies the same, not a convolution, but it goes through the whole image in the same way. And it considers the local similarities of those patches together. And how it does that, it does it using the mean and basically the variance of those smaller patches. Now, the C1 and C2 constants are constants to make sure that there's no numerical error in this. But it basically, and 11 by 11 is a typical patch that is used, but I believe that's something, a hyperparameter that you can adjust. And one of the libraries that you can use is scikit-image. Now it's more of a scikit-learn, but more for image kind of pre-processing stuff. And that's available over in that package. Again, usage is similar to scikit-learn, I believe. That shouldn't be too difficult. But basically, if you have X and Y as two images, what it does, it gets basically the average of the mean and variance in local patches over those two samples that you are inputting. And it's a good measure to measure the similarity between two images if you have pairs. So not all of the times you have access to the ground truth pairs when you are trying to generate samples, but if you do, this is a good measure to see how close they are, and put a number on it. Again, another note, this is sometimes also used as a loss function when you are trying to generate good segmentations, for example. And as I mentioned, there's further reading materials if you're interested, and I think that's basically all for the computer vision tasks. Now, the final part of metrics that we want to talk about, and I know we are at 2 p.m., so this is going to be quick, maybe 5 to 10 minutes, hopefully, but feel free to leave if you have other commitments. Otherwise, of course, welcome to stay. This is being recorded. So in NLP, depending on the task, again, as was the case in computer vision, you could go back and use classification metrics. For example, if you are using sentiment analysis, which is basically classification task, entity recognition, another classification task, Q&A, if you're answering in a single word or single token, that's another classification task. So those metrics that we defined are applicable. The things that we want to talk about here is specifically, for example, when you're generating something, as in machine translation or Q&A, when you're generating a sentence, or I think it's called open Q&A or something. Image captioning, video captioning, where you're generating a caption. So whenever you generate a language, you want to compare that with a reference and see how basically close to the sentence, for example, that you are trying to generate, how close you are to that. Human analysis, and as always, is an option. You can have human to check those references and see if they are similar enough, if they carry the same message. Again, this is one of those challenging tasks. There's lots of I have to correct myself, I don't know if lots of, but there is significant amount of research going around finding good metrics to be able to compare these the different languages that the model your model is predicting. But we're going to see maybe the common ones, which of course they have also pros and cons. So in language, you want to basically let's look at this example that you have here. So if your candidate that you have generated is this one, 7D, and then you were supposed to either predict reference 1 or reference 2, then one way to compare these two that back in the days maybe people used to do, even at the moment it might be good a starting point again. One of the metrics that might help is the precision. And how to do precision is basically compare these two sentences, reference 1 with the candidate and reference 2 with the candidate, and see how many of the words that you have predicted are considered true positive, in the sense that they exist in one of those references. So I think this is I need to fix this. This is not modified precision. Now we are still talking about the precision, and then we have modified precision here. So original precision is, of course, just calculate the true positive. And the way you do it, for example, if you're using unigrams, then again, these n-grams are the way that you tokenize these sentences. If imagine you're using unigrams, then it basically is counting the number of true positives. And as I mentioned, if your predicted word exists in one of those references, it is considered as a true positive. And you should basically instantly see that this is a big problem, because you're just comparing the existence of words, not their location, not their basically the proper usage of grammar or everything else. But if you're doing that, basically 7 is the 7 times that you have a true positive, and all of them basically they were true positives because you had the on every one of these references. So then you would get 100% precision if you do simple precision that we talked about. And of course, this is basically a very low performing model. It is not predicting anything useful. One way to solve that a step forward from the original precision is modified precision. And what that is basically you, I think you get the maximum of the number of times that your basically your predicted word exists, not counting it all the times. So for example, here in two references, in one of them we have 2D, in the other one D, and in the other one we have 1D. So we consider that the number of these that was all right to predict as 2, which is the maximum of the existence between the two references. And then in that sense, we will have 2 basically true positives, and the rest, all of the basically true positive and false positives rates would be 7, because we have 7 predictions. So out of the 7 that we have predicted, 2 of them are considered because that's the maximum. So we just clip the true positive by the maximum number of matches, and that is more representative. But you could still see that the main problem is still there. And this is a good example. So how to get 100% by predicting by having a low performing model. So if your prediction is of D, let's say, and your references of these long sentences, now without getting distracted by the length of the sentences, what happens if you want to get the precision, the modified precision, unigram precision, is that you will have one of, and the maximum number of that in all these 3 sentences is 1, I believe. And then you will have one of those in the prediction, and then the maximum is also 1. So what it means, you will get 2/2, which is 100% precision. And you could see this is not a good job. One way that people try to overcome with this problem was basically essentially putting a weight on the short sentences. So people want, for example, saw that, okay, it could be fooled with short sentences, but if the difference between our sentence, the predicted sentence, and the reference sentences is very large, if that gap is very large, then we should weight that. For example, here we're predicting 2 words. Let's say we're supposed to predict 10 words. So that should be a low score rather than 100%, even if the precision, the modified precision is giving us a good score. And the way to do that is using this blue score. And what it does, it basically gets the geometric mean of these specific, the modified precisions that we have. So that's the same thing. It's just geometrically averaged over the different words. But what is kind of more important and more novel here is this brevity penalty. And what that does is that if the predicted length of, if the length of the predicted sentence, or the translated length, if you're talking about machine translation, is C, and if the reference length on, now you might ask, is it average, is it the maximum? People use different things, I believe. Most of the times they use the maximum among those references. Let's say if this R is the maximum and your prediction is C. If it is more than that, people say, okay, that's 100% weight. You would get a 1 weight for that precision. Again, it should be clear that there is one problem here if you are predicting too long sentences, but there is no basically mechanism to stand for that here, and that's one of the downsides. That could be one of the downsides of this metric. And then if your sentences are shorter, the shorter than that R length, that reference length they are, the less the weight that they get using this exponential of 1 minus R over C. So basically the smaller the C gets with respect to R, you would get a higher value here, and because it's a negative high exponential, then it means the overall score would be smaller. This value, the total value of this would be smaller. And then you would weight that, multiply that by the precision. This specific metric and a few other metrics are available in both Hugging Face and NLTK libraries if you want to use them. I have put a few different further reading references. So in order to solve some of the problems that we talked about, those metrics, there are more recent methods, specifically glue and generalized glue. And the glue, these two are different. Of course, the second glue is Google Glue. And so there are other metrics that if you want to refer to, and these two libraries have most of them available if you want to use. And That's the end of today's session. Is there any questions? If not, or if there is any questions, like always, happy to answer over the discussion forum. Was there any question?
Hi, Marty.
Yes.
I'm the student who presented about the coffee quality